So now that we know how to solve quadratic equations, we're going to start using all of our new information, our new abilities, to begin to graph quadratic functions. Now remember, quadratic functions generally are written in the form of y equals ax squared, meaning they contain an x squared term, and the x squared term is the largest term in the polynomial. Another way to look at them, or another expression for polynomial functions, is the standard form that includes not only a quadratic term, but also a linear term and a constant term. So we want to look at the graphs of these functions now, and there are multiple ways, just as there are multiple ways to solve quadratic equations, there are multiple methods for graphing them depending on the form of the equation that we receive or that we're given. So let's look. If I were to graph this very first one, and suppose the number a equals 1, I would have a curve that looks like this. This is the standard position for a quadratic function. If a equals 1, we can tell just by inspection that if I put 1 in for x, 1 squared is 1 times 1, which is what we've decided a would be, gives me an output value of 1. On the other side, if I were to put in -1, well, -1 squared is +1 times the 1 we decided we'd let a be in this case. I get the same output. That's the reason for this shape that reflects across the y-axis. Now, I just used a bunch of lingo. That's all lingo you need to get comfortable with, but let's go and break it down a bit. So the shape of a quadratic always has this curve, kind of a little U-shape curve. We call this a parabola or a parabolic curve. So the shape is always going to be a parabola. It may face different directions. For example, I could have a parabola that faces down this way. That's a possibility. But no matter what, the curve or the shape will always have a parabolic curve if I'm graphing a quadratic function. Always. The reflection refers to the fact that whatever's happening on the right-hand arm, this is called an arm. Both of these are called arms. One is a left-hand arm and one is the right-hand arm. Whatever the output is for some value on the right-hand arm, the left-hand arm is going to have the exact same output value, though not necessarily the same input value. Notice that I have -1 and 1. These are not the same inputs. They are opposites of each other, but it's possible for a quadratic to look like this. That's not the one I want. It's possible for a quadratic to look like, for example, that's also not the one I want. Let me go again. Say it looks like this. So notice what's happened is, say my input value is -2 in this case, and my input value would be negative, let's say 4. My input values are different, but for this curve, the output value is still 1 in both cases. So we're looking at the output values on each arm is the same if we were to draw a horizontal line through the graph. Meaning, if I drew a horizontal line, say this way, on my orange graph, my output would be whatever this value is on the y-axis, and my output would be the same on the other arm. If I'm looking at the pink graph, my output and my output would be the same. And the other word I used is reflected, or reflection. Quadratic graphs have a reflection over some midline or a line of symmetry. And the line of symmetry in the first two cases, in the pink case and in the green case, the line of symmetry is the y-axis. And if we look, the distance from the y-axis to each point on either side is exactly the same. So in the case of the green one, if I were to take some place on the y-axis, the line of symmetry, the distance to the left to get to the graph is exactly the same as the distance to the right to get to the graph. Same thing here, only the line of symmetry on the orange graph is not the y-axis. It's some other line through the x-axis, some other vertical line. But still, the symmetry is the same. The distance to get to the point on the right-hand side from the line of symmetry is exactly the same as the distance to get to the left-hand side. Same thing in this case. Distances are the same. So the output or the rise part of it, the output, is the same on both sides of the graph. And the distance from the line of symmetry is the same on both sides or both arms of the graph. So that was a lot of stuff. I'm going to do some examples, and while I do, I want you to pay attention to the fact that the graph has a parabolic shape, that there are two arms, and that the two arms serve as a reflection over the line of symmetry. So these are all words that you need to get really comfortable using in reference to quadratic graphing or graphing quadratic functions. Now we do have an equation that we need to work with, and it's relatively simple. It's a formula to find the line of symmetry. So given f of x equals ax squared plus bx plus c, the line of symmetry is always the line x equals the opposite of b divided by 2 times a. So we're going to find the line of symmetry, meaning the x input, the input value for the line of symmetry, and then we're going to graph additional points to see the shape. Let's do an example. Let's graph y equals x squared. So this is called the parent form. So the parent form of a quadratic, parent forms are going to become more and more evident as we move through algebra, or it'll be used in more and more different cases. In the form of a quadratic, what we mean is it's the most basic stripped down. The linear term, b would equal 0, so it doesn't exist. C would equal 0, so it doesn't exist. And on the quadratic term, a equals 1. And so we're left with the parent form of a quadratic. Now let's graph it. Let's get this moved. And we're going to graph first by using the formula for the line of symmetry. So in this case, if I wrote this out with my a's, b's, and c's, I would have y equals 1x squared plus 0x plus 0. So this is the standard form of the parent equation. 0x because we don't actually have a linear term, and 0 for the c because we don't have a constant term. And of course we do have a quadratic term with apparently no leading coefficient, which means the leading coefficient is actually 1. So we want to make a table, but first we want to find the center of the curve by using this formula. So x equals minus the opposite of b, so the opposite of 0, over 2 times a. It's defined because I don't have 0 in the denominator, but clearly x equals 0 is the line of symmetry. Now, once I have the line of symmetry, I'm going to actually dot it into my graph. So I'm going to dot it in. The line of symmetry is the line x equals 0. And then I want to make a table of input and output values. And at the very center of my table, I'm going to put my line of symmetry input. So when x equals 0, what is y equal? Well, and I don't want to use this table. Let me take this back. I want to use this form just because it's easier to work with when you're actually plotting values. So y equals x squared, that's our function. and what's our output is going to be y. So here in the center of the table, I'm going to put my line of symmetry in. Y equals 0, x equals 0, and so when x equals 0, y equals 0 squared, which equals 0. And so I know I have the point 0, 0, or the origin on my graph. And now I want to pick a couple of points on either side of the line of symmetry. So how about we choose -1 and -2, and let's choose +1 and +2, just to get a feel for what happens to that graph on either side, what's happening to the right-hand arm and what's happening to the left-hand arm. Y equals -1 squared, which equals 1, and y equals -2 squared, which equals 4. Down here, y equals 1 squared, which equals 1, and y equals 2 squared, which equals 4. And you can already sort of see that reflection across the line of symmetry where the outputs are the same. Different inputs, but the same output. So let's graph these points or plot these points. -2 input leads to 4 output. So let's say -2, 1, 2, 3, 4. So that's the point, -2 and 4. -1 input leads to 1 output, -1, -1, and 1. And then on the other side, the input of 1 leads to the output of 1, and the input of 2 leads to the output of 4. So I have 2, 4, and 1, 1. And if I connect these, I get the parabolic curve. Any horizontal line will give you 2 outputs for the curve, and the outputs are exactly the same on either side. And the axis of symmetry is identified as the line x equals 0. Let's do another example of graphing a quadratic using a table. So I want to graph y equals, let's say, 2x squared. So again, I'm looking at, and let's see if I can paste in a graph real quick. There we go. Uh-oh. Sometimes there we go. All right. So again, I'm looking at y equals 2x squared plus 0x plus 0, and obviously there's zeros because they don't exist here. So this is the parent graph that I'm multiplying times 2. So first thing I want to do is find the axis of symmetry. So x equals the opposite of b over 2 times 2a. So that equals 0 again. So once again, my axis of symmetry is the y-axis, and I have to label that. That is the line x equals 0. And now I want to make a table. And I want to put 0 in the middle because that's my axis of symmetry. So y equals 2 times 0 squared, which equals 0 squared is 0 times 2, which still equals 0. So notice that multiplying by a doesn't change my y-intercept, or the place where the curve crosses the y-axis. That's an interesting thing to take note of. But does 2 change my other values, my output values? Well, let's go -1 and -2, +1 and +2. So y equals 2 times -1 squared, which is 2 times 1, which equals 2. Y equals 2 times -2 squared, which is 2 times 4, which is 8. And then y equals 2 times 1 squared, which is 2 times 1, which equals 2. I look like I'm getting that reflection again. Y equals 2 times 2 squared, which is 2 times 4, which is 8. So now I want to plot these points. Now I need to be a little bit careful. The -2 has no trouble fitting on the x-axis, but 8 is a pretty big number, so I need to change my units on the y-axis. So let's see, I have 1, 2, 3, 4, 5, 6, 7. Darn, I have almost enough. We're not allowed to graph off of a table, off of a graph, a grid, right? So I'm going to take 2, 4, 6, 8. Okay, so -1 and 2. -1 and 2. I've chosen my units to be worth 2. So I have -1, 2 is a point. -2, 8. -2, 2, 4, 6, 8. -2, 8. 1, 2. So at x equals +1, y equals 2. That's the point 1, 2. And 2, 8, +2, 2, 4, 6, 8. 2, 8. If I connect those dots, I get something that looks almost exactly the same as the graph above. So I get, let's compare this. I ended up with a parabolic curve. I have a right arm and a left arm that each serve as a reflection across the line of symmetry, and I have a line of symmetry that I found from my formula. And so this is always true about a quadratic graph. So we're going to learn about some other changes. For example, this one that flips over and this one that moves over. We're going to learn about some changes on quadratic graphs. Also, we're going to learn about squeezing and stretching, which if you look at these, even though my units aren't quite the same on the graph, you can kind of see that this one is a bit squeezed from this one. If I were to graph both of these on the same plane, you'd find that this one is really squeezed in comparison to the first one. But we'll talk about that a little bit in the future. The important thing is a quadratic graph has two arms. The arms reflect over a line of symmetry. The line of symmetry can be found by the equation x equals -b over 2a. And when you're finished, the shape is a parabola.